So we finished our discussion with structure of the ribosome, that there are two different ribosomes. We figured out why transcription and translation become one continuous process in prokaryotes. And the next step would be to chat about genetic code. I already told you, concepts that we talk about in this unit are fairly abstract. You have to embrace it. So what is genetic code? If people use different analogy for DNA / RNA in a protein, your nucleotides are the words. Sorry, the letters. Nucleotides are the letters. And in order to convey message, letters must be organized in words, and words must be organized in sentences. Do you agree with me so far? So, it turns out genetic code is the language that we use in describing which amino acid will be incorporated in a certain place of the protein. And it turns out that this language consists of 64 words. You can see all 64 of them in this table. So they're grouped by the first, second, third letter. Okay? So if you find a sequence of 3 cytosines, it means proline. Okay? If you find 3 adenines, it means lysine. That makes sense? Now, why 64? Why not 61 or 72? Yes. No, not 4 amino acids, 4 nucleotides and groups of 3. Why not? Okay, why can't we have like 2-letter words? Why can't we have this, each individual word, quote unquote word, it's called a codon. So like GAC is the codon for glutamic acid right here. Why not 2-word, 2-letter? Can we use 2 letters? Why? No. I mean, like, fundamentally, like, why? What is a very simple reason why code has to be 3 letters? Why 64? Why not 10? Let's start with this. Why 64 codons and not 10 or 11 of them? Each codon has to match what? A certain, like if I tell you CUA, what does that mean? It means leucine, right? So each codon, it is assigned to a specific amino acid. Okay? How many amino acids do we have? I would argue about 21, strictly speaking. Okay? There's some evidence that we have 22. Okay, 21. Let's stick to 21. 21 amino acid. Now, if you have 2-letter codons, how many codons in total you can make out of 4 nucleotides? You have like A, G, 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 C, C. How many words like that you can make if you have only 4 letters? That's the math question, I know. That's why it's not going to be on the exam. How many? Here's, nope, it's much simpler. Duh. No, wait a minute. I will teach you how to do things like that. It's very easy. Do you use code locks? Like the lock that has a code on it. Let's say 3 numbers, okay? So on each dial, how many numbers? 10, from 0 to 9, right? Now, what will be logically the first combination? All zeros. Second, 001, 002, how many combinations? What is the last combination? 999 plus all zeros. So how many combinations? 1,000. What, again, how many numbers on each dial? Numbers in each 10. How many dials? 3. Now link 10, 3, and 1,000. What is the 1,000? 10 in the power of 3. Seriously, that's the trick. That's how it works. So if you see a lock with 6 dials, good luck getting the combinations. Okay, and if each dial has 26 English letters, it's 26 in the power of 6, you will never get the code. It's going to take you like forever. So if we have 4 different letters in 2 possible positions, 4 in the power of 2 will be 16, which is not enough to encode 21 amino acid. Now, if we have same 4 letters, but 3 positions, 4 in the power of 3, 64. We have 21 amino acid. What does that mean? Look at the table here. Each amino acid, or most of them, will be encoded by more than 1 codon. This is called a degenerate code or redundant code. Pretty much it means they have synonyms, okay? Like leucine, okay? They have like what, 6 different codons that mean leucine. And you see the differences in the last 3 letters, last third letter here, and the first letter here. Okay. Now, if you think about this, it kind of decreases the role of mutations, right? Because if U here is changed to C, it's still going to be leucine. It's not going to affect the protein structure. Does that make sense to you? Synonyms, okay? Some codons have other function. We have 3 codons here, UGA, UAG, and UAA. You don't have to memorize them. You're not going to get a question. Which of the following codons encodes for leucine? God forbid. Okay? Or which is the starting codon? Interestingly enough, there's one starting codon here, AUG, and it's very convenient. Because by looking through, you can always say, there's likelihood the protein will start here. AUG at the same time encodes for the first amino acid. In every protein, first amino acid is always methionine. Always. You can see that some amino acids are encoded by just one codon, and some of them are encoded by multiple codons. Okay? Does that make sense so far? Yeah, every protein, every sequence of mRNA, every gene, well, gene will start with ATG. Does that make sense? This is ATG. but the mRNA sequence will start with AUG. Does that make sense? The concept that I struggle with when I explain is the concept of the codon and anticodon. Let me explain it as it is, and then if there are questions, we will try to play around it. So you have mRNA, mRNA that consists of nucleotides. Does that make sense? You agree with me? It's nucleotides. And when you read the sequence of those nucleotides, you read them by triplets, by codons, like AUG, CUC. Each triplet means specific amino acid. Now, these amino acids, they have to be matched to those codons. And the role of the matching belongs to tRNA, the transport molecule that has that cloverleaf structure. So among those cloverleafs, there are two parts that I want to focus your attention on. One part is the site where amino acid attaches to. You see? Here. It's a part of the molecule to which amino acid sticks. Another part of the molecule has so-called anticodon. Anticodon loop has a sequence that specifically recognizes the codon. So let's take a glance at this one. So the codon is shown here on the purple line, and it's GCC. Let's find which one is that in the table. So GCC is right here. It encodes the amino acid alanine. Do you agree with me so far? Is that clear? Is that clear? So the transfer RNA that has sequence complementary to GCC, which is going to be CGG. Does that make sense? Why it is CGG? It's complementary. This amino acid, this tRNA will carry the alanine molecule on its tail. No? You don't get it? It's okay. I'm asking if it's okay or not. Yeah. The what? So each tRNA has amino acid on its tail. Okay? But it's not that. So tRNA with this anticodon will always have alanine. It's not going to have anything else, only alanine. If we would look at the tRNA, so tell me the anticodon for UUU. What will be the complementary sequence? AAA. Okay. So if we have tRNA, okay, which has AAA as anticodon, it always is going to carry phenylalanine on the tail. Yes. So you're going to have how many tRNAs? Look at the table. Slightly less. 60. We have 3 stop codons. 61. We're going to make 61 different transport RNA. Does that make sense? So there's going to be 1 transport RNA for each with each and every anticodon that will recognize each and every codon. Does that make sense to you? So this is very fundamental idea, right? That makes sense? So this tRNA will be hauling amino acids to the ribosome in order to put them in the right place where codon is. That makes sense? We're getting to the point where we will realize how it all happens. Okay? So this is protein synthesis. It's usually when I explain it, first I'm going to explain it with words. And then when I will see the complete shock, awe, and a total lack of understanding in your eyes, we're going to do a little play right here. Huh? Say again? Well, something like that. So I will need a few volunteers, okay, to play along with me. All right? Okay. So what happens? It all starts with a small subunit of the ribosome. It recognizes the special sequence on the mRNA located before the start codon, which is called a Shine-Dalgarno sequence. Okay. Shine-Dalgarno sequence specifically in prokaryotes. In eukaryotes, it's the special structure on the 5' end of the mRNA. Okay, so small ribosomal subunit recognizes that initiation site, okay, and binds to it. All right? Next, we have first tRNA. You see, which has anticodon UAC, which matches the start codon AUG. Does that make sense? Okay. So we've got mRNA, small subunit, tRNA. And last, the large subunit binds to it. So now we've got the initiation complex. Everything is assembled. We can proceed. Are you staying with me so far? Now, large subunit, well, the ribosome overall, has 3 specific sites for translation. A site, B site, and E site. To make it kind of easier, you know, you can remember A site, which is right here. So A, P, and E. Okay. So what? Huh? You can say it's fine. Now, A means attachment. P means protein or peptide. E means exit. Now, that means for me and means for I kind of give you an idea how you can remember, because it directly relates to the function of those sites. So what happens first? The next amino acid enters the A site. So tRNA with next amino acid enters the A site. That makes sense? You have your polypeptide in the P site. Next you have a transfer. You see that arrow here? The entire growing chain is transferred to the new amino acid. You see? It looks really ridiculous and inefficient. So it's not one molecule that's attached to the end. It's the opposite. Entire molecule is attached to the next amino acid. All right? Actually, this activity is called peptidyl transferase, peptidyl transferase is the enzyme that catalyzes this shift. And this enzyme is actually RNA. So then, what you end up with is the growing chain for a very short period of time in the A site because of that transfer. Okay? Release factor kind of kicks out the growing chain back in the P site. Okay? The old tRNA leaves from the E site. That makes sense? And in the end, another release factor stops the translation at the stop codon. That makes sense? Let's take a little pause. I need volunteers. It doesn't make any sense, I know. It really doesn't. Stop codon is the part of the sequence. Does that make sense? It's like, you know, like when you read the chapter of the book. You know exactly where it's, you read the sentence. You know the capital letter is where it starts, and period is where it ends. So this AUG codon is a capital letter. This UAG is the period at the end of the sentence. Does that make sense? Your question, Chen? Wonderful question. Okay, and second question that Dominic has, is that a cancer? First, generally speaking, cancer is when your cells divide without any limit. It can be caused by a ton of things. Now, so it may cause cancer, but not necessarily will. Is there a situation when stop codon doesn't stop? The very short answer is not really. Only if stop codon, I explain why it is almost no, but I will explain the exception. If stop codon is changed, then we're screwed. Okay? Because you continue to read. Takes the period, well, or takes it out completely. Just, which will be mutation, yes. But in this case, you don't have a stop codon anymore. Now, there's one exception, which I was about to say. Remember I told you that for a long time we were taught, I was taught, you were taught, there's 20 amino acids. 21. I mean, let's not jump to 22nd. I read about 22nd, but 21. 21st is selenocysteine. It's an amino acid that contains selenium. Interesting thing is that selenocysteine is encoded by the codon that is UGA. It's a stop codon. Now look, if downstream, where's my pen? Downstream from the stop codon, right here, there's a special sequence called SEC, selenocysteine insertion sequence. If it's behind it, it says, dude, no, it's not a stop codon, proceed. Does that make sense? So it's a special additional structure of RNA that alters the function of that codon. Does that make sense? That's the only exception when stop codon is not a stop codon. Only selenocysteine. It's for some reason is encoded by that stop codon. Oh, it will stop on some other. So pretty much it's the thing, like, you know, you're driving, okay, and you have a sign, the road is closed. But then there's a policeman that kind of shouts at you, no, it's fine, proceed. You continue, and then at the end, you have a definitive sign. Yes, the road is closed. You see the difference? Okay, Now, couple more things. First of all, obviously this process requires an enormous amount of energy. I don't include the regulatory factors that control the translation process. I don't include all the energy molecules, GTP, that is used as the energy source. There are plenty of them. I want you to know the translation at this level and how fast it goes. 0.05 seconds per amino acid. Considering that the protein, like good average protein, can be, say, 200 amino acids. It's rather small, actually. What we talk about, 10 seconds, you have a protein molecule. 10 seconds, you have a protein molecule. Now, remember this. Remember, you have a ton of mRNAs and ton of ribosomes on them. So just here, I can count 11, 18, something like 27 protein molecules being made at the same time. So in minutes, you can accumulate millions and millions of protein molecules in the cell. Well, probably not millions, but thousands, definitely. Does that make sense? Okay, we're going to call it a day, and I will see you on Monday.